How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at 16.6 practice problems for weak acids. So here we have number one. The Ka of hypochlorous acid, given by this formula, is 3.0 times 10 to the minus 8 at 25 Celsius. What is the percent ionization of a hypochlorous acid in a 0.015 molar aqueous solution at that temperature? All right, so first off, we know that the Ka expression is going to equal the H plus ion concentration times the ClO minus ion concentration all over the HClO concentration. So now the question is, well, what are those things? So let's write it out. We start with HClO in equilibrium with H plus and ClO minus. And we know that initially the HClO is 0.015 molar. And H plus is 0 and ClO minus is 0, right? We're going to set up an ice box. Initial change equilibrium. So a certain amount X is going to dissociate. So that's our change for HClO. It's minus X. For H plus, we end up with more of some amount X. Same with ClO minus plus X. So at equilibrium, HClO is 0.015 minus X. H plus is X, ClO minus is X. So now I can plug and chug this into my Ka expression. Ka equals X times X all over 0.015 minus X. So now we're going to do a little algebra and get it into the ax squared plus bx plus c format. So I end up with Ka equals x squared over 0.015 minus x. Let me times both sides by the denominator. So I end up with x squared equals Ka times 0.015 minus x. And if I distribute that, I end up with some numbers. Let's see. I do a little algebra. I'm going to skip that step. You all know how to do that. And I end up with x squared minus Ka times x. No, it's plus Ka minus whatever Ka times 0.015 is. So when I multiply that together, I end up with 4.5 times 10 to the minus 10. Now I plug it into the quadratic equation. And, that being x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is 1, b is Ka, and my c is this negative 4.5 times 10 to the minus 10. And when I plug and chug that, I end up with x equals 2.12 times 10 to the minus 5. So that's how much has dissociated. What we're trying to get is the percent ionization. So the last step is, well, we know the percent ionization is going to equal to the amount that ionized, 2.12 times 10 to the minus 5, divided by how much was there originally, 0.015 times 100, because it's a percent. And when I plug and chug that, I end up with 0.14% as my answer. All right. Number two, of the acids in the table below, which is the strongest acid? So strongest acid means the biggest Ka value. All right. I think all these are weak acids, so it's asking which is the strongest weak one. So we got to look first at what the power is. So now you might be thinking, hey, the biggest one, I want the biggest number. But you got to remember these are negative powers. So I can immediately go, hey, I want the least negative power. So I have minus 5, minus 4, minus 8, minus 4. So I can get rid of these minus 5 and the minus 8 because they're smaller than 10 to the minus 4. So now, again, I'm looking for the biggest Ka. Well, let's see. Which number is bigger, 1.8 times 10 to the minus 4 or 6.8 times 10 to the minus 4? And it's this one, 6.8 times 10 to the minus 4, which gives me choice D, HF. So out of all those, HF is the strongest acid. All right, number three, an aqueous solution of HZ, some weak acid, is prepared by dissolving 0.04 moles of it in enough water to make 2 liters of solution. The pH of the solution was 4.93 at 25 Celsius. What is the Ka? So we can start off, well, I know Ka is going to be my H plus times my Z minus all over my HZ, right? Because generically I have this weak acid and it's going to partially ionize to give me H plus and Z minus in solution. So that's where I get my generic Ka expression. They tell me that the pH was 4.93. So I know from that I can figure out my H plus ion concentration because pH equals negative log of my H plus ion concentration. So if I rearrange this to solve for H plus, I get H plus equals 10 to the negative pH. So I plug and chug, I get 10 to the negative 4.93, and I end up with, where did I write that number down? 1.17 times 10 to the minus 5 molar as my H plus ion concentration. Now, my H plus ion concentration is also the same concentration of the Z minus. And my HZ is going to be the original molar solution minus X, right? So, well, 0.040 moles over 2.0 liters is going to give me 0.020 molar as my initial concentration minus X. So now I can plug and chug. My H plus is 1.17 times 10 to the minus 5. And so is my Z minus, so this is really just getting squared, divided by my original molar concentration of 0.020 molar for HZ minus that 1.17 times 10 to the minus 5. Now remember, if you're using a calculator, you gotta make sure that you have parentheses around the denominator thing, so it knows, hey, these go together. And when you plug and chug that, you end up with 6.84 times 10 to the minus 9 as your answer for that one. All right, number 4. In which of the following aqueous solutions does the weak acid exhibit the lowest percent ionization? So, least dissociated. Which one of these will dissociate the least amount? Which means it is the weakest acid. So now, what's nice is you look, all of these options have the same concentration. So we don't have to worry about what their concentration is and how that influences the percent ionization. We could just look at the Kas, and we're looking for the weakest one. So I got first to look at 10 to the, so I have 10 to the minus 5, to the minus 4, to the minus 4, to the minus 8. And I can eliminate, I just look on that. I can look and go, hey, this one is the weakest acid because it is the smallest number, just looking at the power of 10, right? So that's that one. All right, number 5, the pH of a 0.6 molar aqueous solution of formic acid at this temperature is 1.98. What is the value of the Ka for formic acid? So again, it's a weak acid, so I start with the molecule, it's in equilibrium with an H plus and the rest of that anion, HCHO₂ minus. So the Ka expression is going to be the concentration of H plus times the concentration of that anion, HCHO₂ minus, all over the concentration of HCHO₂. So now if I were to do an icebox for this, which, maybe I shouldn't have written, whatever. All right. I probably could have wrote it over here. Anyway, I do an icebox. I start with 0.60 molar and 0 and 0 for my HCHO₂, and the H plus and the CHO₂ minus. Some amount of it dissociates, giving me the same amount but of H plus as well as the same amount of CHO₂ minus. So at equilibrium, the HCHO₂ is 0.60 minus X. And we got X and X for H plus and the anion. Right? Now what is X? Well, they tell me what the pH is. It's 1.98, and I can use that to solve for my H plus. So I know pH equals negative log of the H plus ion concentration. So if I rearrange to get my H plus and solved for that, it is equal to 10 to the negative pH. So I can plug that in. I get 10 to the negative 1.98. And as a number, what do I get when I do that? Beep, bop, boop. I get 1.05 times 10 to the minus 2 molar. Now that is my X. All right, that is this number, that is this number. It is the X here, so I can now plug and chug into my Ka. I go, all right, it's 1.05 times 10 to the minus 2 times itself, so it gets squared, divided by, well, what was the initial concentration? 0.60 molar minus that X value, 1.05 times 10 to the minus 2. And when I pick up my handy dandy calculator and beep bop, boop, I end up with 1.87 times 10 to the minus 4. Okay. Number 6, what is the pH of 25 degrees Celsius of a 0.02 molar hypochlorous acid solution? The Ka is this. So we want the pH. Okay, interesting. Well, I know that pH equals negative log of the H plus ion concentration, so I'm going to have to figure out what is that H plus ion concentration. And all they did was give me Ka. So, all right, I start with HClO, and it's going to be in equilibrium with H plus and ClO minus. So I started with 0.0200 molar and no H plus and no ClO minus, right? I'm going to do an ice box. So how much did it change? Well, some amount of HClO got used up. So minus X, H plus will be positive X, ClO minus will be positive X. So at equilibrium, we have 0.0200 molar minus X for HClO, and X and X for H plus and ClO minus. Now they give me my Ka. So my Ka expression is going to be that concentration of H plus times the concentration of ClO minus all over the concentration of the HClO that did not dissociate. So now I have my equilibrium values. I can plug in for X. Well, H plus is X, and ClO minus is also X, so it's really X squared divided by, and at equilibrium, the HClO is going to be the 0.0200 minus X. So now I do a bunch of algebra, and I rearrange to get it into the AX squared plus BX plus C format. And what do I get? I got X squared plus Ka times X minus Ka times 0.0200. And when I actually plug those numbers in, let's see, my TV movie magic, I have 6 times 10 to the minus 10. So now I use my quadratic. My A equals 1. My B equals my Ka of 3.00 times 10 to the minus 8. And my C is equal to a negative 6 times 10 to the minus 10. So I use that quadratic, the whole, X equals negative B plus or minus the square root of B squared minus 4AC all over 2A. And I get X equals 2.45 times 10 to the minus 5. Now that is my X. I'm not done yet because the question is asking for pH. I just solved for H plus. So now I got to plug it in. Right? pH equals negative log of that 2.45 times 10 to the minus 10. And I end up with, I'm sorry, it's not 10 to the minus 10, it's 10 to the minus 5. Beep bop, boop. I end up with 4.61 as my final answer for the pH. All right, number 7. It says the acid dissociation constant of sulfurous acid, H2SO3, or Ka1 for the first H plus is 1.7 times 10 to the minus 2, and the Ka2 for the second H plus, because it is a diprotic acid, we got 2 H pluses, is 6.4 times 10 to the minus 8. Calculate the pH. All right, well, first things first, we got to look at the value for these Kas. So if we take a look, they're significantly different. They're different by like a factor of 1,000,000. Like you can think of it as for every 1,000,000 of that first H plus, then you get 1 of the second H pluses. So if we're trying to calculate the pH, we can ignore entirely the second H plus because it is so much smaller than that first one. You know, it'd be like, hey, we have this ocean full of water, but we added a thimbleful. How much water is in there in the ocean now? And you would just be like, we can ignore that thimbleful because it's not making a huge difference, right? So that means, hey, let's take a look then just at that first H plus. So we have H2SO3 in equilibrium with H plus and HSO3 minus, right? So initially, you know, let's make an ice box. My initial concentration of H2SO3 is 0.163 molar, and for H plus it's 0 and HSO3 minus it's 0. We use up some amount of H2SO3, so minus X some amount, and we'll create some amount of H plus and some amount of HSO3 minus, so plus X for those. So at equilibrium, H2SO3 is 0.163 minus X, H plus is X, and HSO3 minus is X as well. So now we go, all right, well, what is my Ka expression? Well, I know my Ka expression is going to be the concentration of H plus times the concentration of HSO3 minus all over the concentration of the undissociated H2SO3. And now I can plug and chug. I have H plus is X times HSO3 minus, which is another X, so X squared divided by 0.163 minus X has to equal my Ka. So let me do a little algebra. All right, I'm doing algebra. I'm just rearranging, and I end up with X squared plus Ka times X minus Ka times 0.163. All right. When I put those together and I solve now, now I use the quadratic, right? You go, hey, let me use the quadratic. Again, we use that a bunch of times. My A is 1, my B is Ka, and my C is this negative Ka times 0.163. And I end up with my X equaling 4.48 times 10 to the minus 2. So now if I'm trying to solve for the pH, I can go, well, now I plug in pH equals my negative log of my H plus ion concentration. So I plug that in, negative log of that 4.48 times 10 to the minus 2. And I end up with a final answer of 1.35 as my pH for that one. All right. Number 8. A solution of acetic acid is 2% dissociated at 25 Celsius. What was the original concentration of acetic acid solution? The Ka at this temperature for acetic acid is 1.8 times 10 to the minus 5. I like these problems because we got to use two different equations and make them work together. So they told us the percent dissociated. So I know the percent is equal to the amount that dissociated, let's just call that X, divided by the original amount, M1, times 100, right? So that is the percent ionization. We also know that the Ka is going to equal, the H plus times the anion for acetic acid all over the amount of acetic acid that did not dissociate. So now we gotta figure these out. Well, my H plus is X, right? How much did it dissociate? I got some amount X, which means I also got some amount of A minus all over. Well, hey, whatever the original concentration of acetic acid was, minus how much dissociated, right? Some amount dissociated, broke apart. That's my X. So my equilibrium concentration of HA is the original concentration minus X. So now we have two variables and we got two equations. And I got to think, well, what am I trying to solve for? I'm trying to solve for the original concentration in molarity. So let me replace X with M1. So let me rearrange this. So, all right, well, I get percent, let's see, times 100. Oh, wait, no, I'm sorry, not times 100. It's percent divided by 100 times M1 equals X, right? Just rearrange this to get X by itself. I had to divide each side by 100 and then times by the M1. And they tell me the percent dissociation is 2%. So it's really 2 divided by 100 times M1 equals X. And if I were to just put that in decimal form, it's 0.02 times M1 equals my X. So let me just plug it in. All right, well, I get my Ka equals 0.02 times M1 squared, because it's X times X, divided by M1 minus 0.02 M1. So when I do that, it's the same as saying, well, let me distribute that squared. I end up with 0.0004 M1 squared divided by, well, hey, what's 1 minus 0.02? 0.98 times M1. So now this is kind of easy. This M1 cancels out one of those M1s, and I do a little math here, and I get Ka equals 0.00408 M1. So if I want to solve for M1, I divide each side by that 0.00408. I cancel that out, and I end up with M1 equaling 0.441 molar. All right, so the hard part here was going, hey, I have two unknowns. They tell me the percent, but I don't know what the original amount is, but I can rearrange to solve for it and plug it into the other equation. Yeah, one more just like that. A solution of formic acid is 3% dissociated. What is the original concentration of the formic acid? So again, they don't tell me what the formic acid is, so I generally just go, hey, I got a generic weak acid in equilibrium with its H plus and its anion. So you go, all right, initial change equilibrium, right? You go initially, I don't know, I had some original molarity and I got 0 H plus and 0 anion. I used up some amount of that weak acid to make the same amount of H plus and the same amount of the anion. So at equilibrium, I have my original concentration minus whatever dissociated, giving me that same amount of H plus that from what dissociated and A minus. So my Ka equals, well, X times X all over the original acid concentration minus X. Now they told me also that the percent dissociated equals 3.0%, and that's going to be however much dissociated, X divided by the original amount times 100. So if I wanted to rearrange a solve for X, I get X equals 0.03 times M1. So how much dissociated? Well, 3% of it dissociated, so 0.03 times however much we started with. So now we can plug this into the Ka, right? We combine those two equations together, and I get, all right, my Ka equals 0.03 M1 squared all over M1 minus 0.03 M1. So when I distribute on the top, I have 0.0009 M1 squared divided by, hey, what's 1 minus 0.03? 0.97 M1. Now this M1 will cancel out one of those M1s up top, and now I can just kind of rearrange and solve for M1, right? I got Ka equals all that stuff, so I get M1 equals 0.194 molar. I hope you found that helpful. I'll see you in class. Goodbye.